Hello everyone, I'm Shaoyu from School of Creative Media, City University of Hong Kong. I'm going to present our recent work FrictGAN, frictional signal generation from fabric texture images using Generative Adversarial Network. This work is collaborated with the University of Tokyo. I want to thank my co-authors and supervisors here. In this slide, I will give a brief introduction on our work, FrictGAN. FrictGAN is an end-to-end system to input the fabric RGB images and automatically generate frictional coefficient signals for rendering the haptic texture of fabrics from the input image. With FrictGAN, users could feel the fabric surface texture from visual stimuli. In this part, we use amplitude spectrogram as a 2D representation of frictional coefficients data, which are similar to time series signals. Our goal is to make humans achieve from seeing to touch fabric texture. Why do we want to give this work? Well, all of us are living in an online Zoom. We could select our preferred products through online shopping platforms, especially now the coronavirus requires us to stay at home, so online shopping becomes more popular. However, the consumers could only see the pictures on the website but not touch them, which is one of the main drawbacks of online shopping. Besides, while VR shopping is another emerging area, it could provide spatial commodities but still missing the haptic feedback. So, how to provide the corresponding haptic feedback of commodities we'll see in the pictures? We give a preliminary exploration of this issue on fabric textures. There is a question how to render the texture of fabric. Generally, the electrostatic tactile display could adjust the attraction between the sliding fingertip and the display surface to create a different lateral force on display. The following research show how to modulate the voltage value to control the friction force during fingertip sliding. When rendering haptic textures based on friction modulation, it is fundamental to know the frictional coefficients data on the card position. However, the frictional coefficients data are difficult for acquisition as two problems. Firstly, most real textures show irregular changes in lateral force on the surface, which makes the frictional coefficients also irregular. Second, it is feasible that we could use the recorded frictional signals data occurred from existing physical textures, but the data collection procedure is usually time-consuming and tedious, and the measured results also depend on the performance of the sensor during measurements. How to solve these problems? Well, the data-driven method could be used for texture modeling and rendering. Firstly, it should be manually collected the frictional coefficient signals to build a database, and then search from the frictional coefficients database to get the target fabric texture characteristics. There are also some works focusing on how to implement the regression model for signal prediction. However, for retrieval-based signals generation, the quality of the database is critically important for the searching tasks. Another problem is that it could not directly generate frictional signals from images and cannot create new haptic textures. How to predict the frictional coefficient signals from RGB images has not been explored. Recently, Generative Adversarial Network has achieved high performance on high-dimensional data such as images or videos generation. Generally, GAN structure owns two parts, a generator and a discriminator. The generator tries to synthesize the fake sample, and the discriminator is for distinguishing the generated sample. Currently, conditional GANs own effective generation performance on cross-modal contents such as from images, text, and audio to images, which could be potentially applied in cross-modal visual to tactile generation tasks. As a preliminary attempt, Uchitoko and Ben presented FrictGAN. or variable tactile signal generation from texture surface images or label attributes using GANs. FrictGAN defines the acceleration-based variable tactile signals as an amplitude spectrogram and trained a GAN-based pipeline to synthesize the spectrogram. Similarly, another work built a cross-modal perceptron based on CycleGAN framework and developed a portable device for visually impaired people. As these previous works focused on acceleration-based signals generation, how about implementing the GAN structure on frictional signals generation? Our work shows the feasibility of generating frictional signals from the texture images using GANs. In our work, we propose FrictGAN, a deep learning-based framework to synthesize frictional signals for electrostatic tactile displays from fabric texture images. Users could input the RGB fabric images to the generator networks, and it will synthesize the amplitude spectrograms of frictional coefficient signals, which could be applied on the electrostatic tactile display to simulate the haptic texture surfaces of the input fabrics. This is one pipeline of FrictGAN. In this slide, I will introduce the architecture of FrictGAN. Our model is built on conditional GAN and Wasserstein GAN structure. Conditional GAN could control the generated results, and WGAN is beneficial for stable training. Well, it is common that there are a generator and a discriminator. The left part is a sample of training fabric texture images passed into the generator, composed by the encoder and decoder. The generator is a unit-based structure with skip connections between the encoder and decoder layers. We add a 15-dimensional random noise vector, which is a green part in the latent space, to increase the variance for the generator training. We combinated the input RGB fabric image and the spectrogram data to the discriminator. We also include the L1 loss between the real and generated spectrograms. After the training stage, we remove the discriminator and only feed the image data to the generator to generate the spectrogram, and then use the Griffiths algorithm to convert the spectrogram data to the waveform signals. To validate the effectiveness of our architecture, we selected HapTest dataset, which includes the visual data and the tactile data for 120 types of fabrics. The frictional data were recorded while a user sliding his or her finger on the real fabric textures. We gave data computation on the current database. For the RGB image, we use size of 1024 multiply 1024 sliding window to move horizontally and crop the original fabric images with the offset of 2 pixels. So finally, we acquired 600 RGB images for each fabric. Refer to the corresponding information between the image pixels and frictional coefficients in HapTest. We also implemented a similar manipulation on frictional coefficients data computation to build one-to-one corresponding relations between images and spectrograms. We used the short-time Fourier transform (STFT) with a 512 Hamming window and 128 hop size for spectrogram creation. In our preliminary experiments, 5 types of fabrics were selected for training to verify the feasibility of FrictGAN. We conduct the data computation method from the previous slide. Finally, we acquired 3,000 pairs of visual and tactile data, and we randomly separated the dataset as 2,000 pairs of training data, 500 pairs of validation data, and 500 pairs of testing data. These pictures show the RGB images, STFT spectrograms, and displacement-series frictional signals. We use this database to verify and evaluate our FrictGAN model. This slide shows our experimental results among the selected 5 fabrics. This column shows input RGB fabric images. The two columns include fake and real spectrograms. Our experimental results show FrictGAN could synthesize realistic spectrograms comparing to the ground truth. And these two columns show the fake and real frictional coefficient signals. In order to show the results more clearly, we adopt a low-pass filter on the signals. The frictional signals after low-pass manipulation are shown on these two columns. We also calculated mean square error MSE values of generated signals and real signals. The MSE values of 5 fabrics are 0.006, 0.005, 0.014, 0.005, and 0.005. Separately, the average MSE value is 0.007. We report the small MSE values to show the reliability and performance of our FrictGAN model. We also identified some limitations that could be improved in future work. Firstly, we only test 5 of 120 kinds of fabrics for our model, so we will include more types of fabrics in our database for training in the future. In addition, for our evaluation, we only calculated MSE values of frictional signals, which could not support the acceptable results from the FrictGAN model. So we intend to conduct ablation studies among different generative models by evaluating some parameters such as a geometry score or FID score. Next, as electrostatic tactile displays need to modulate the driven voltages for rendering the lateral force. As our future work, we will add an additional data-driven regression model to predict the correlation coefficients between the driven voltages and the frictional coefficients. This is to render high-fidelity tactile feedback for the virtual fabric surfaces. Therefore, we will also conduct user studies to collect user subjective ratings on the realness of simulated textures. Lastly, our method not only reproduces haptic textures from known subjects, but also allows users to create new haptic textures from real physical textures or materials. In our future work, we will explore the latent space of the generator and try to build new haptic textures through interpretation. In conclusion, we propose FrictGAN, a deep learning-based generative method for cross-modal frictional signal synthesis. FrictGAN was designed based on the GAN structure, taking the RGB fabric images as the input and the distribution of the frictional coefficients of the fabric surface as the output. We also conducted some preliminary experiments to evaluate the effectiveness of our model. And the results showed that FrictGAN could generate visually similar amplitude spectrograms compared to the ground truth and occur tiny MSE values in frictional coefficient signals. That's all my presentation. Thank you for listening. Welcome to use our code. Feel free to give your comments. Thank you.